After the code that we wrote in the previous video, we can start reading registers through the CLI, and we can even start reading the program counter. So program counter is a special register and it points to the current instruction being executed in a program. And it doesn't actually point to it, it stores its virtual address. We'll get to virtual addresses and how to play around with the virtual addresses. We'll need to create a struct that can represent it. So we'll read the virtual address and create an object out of that struct, and it will basically be a wrapper around the virtual address, and we'll add some methods to it so that we can do some basic manipulation. Okay, so I'll create that file in RDB. So let me close this. So we'll cd into source and then RDB, and right here I will create the file called virtualaddress.rs. And okay, so right here we want to create a struct, so we'll call it virtual address itself. So pub struct, and it needs to be public, so pub struct let's just call it virtual address. And so the address, the virtual address is basically a U64. So we'll create a field address underscore and we'll give it a type of U64. And we'll create constructor for it. And so let's do that. Pub fn new, and we need to return a self from it. So this will be a default virtual address and its value will be 0, adder equal to 0. But if we know the value, then I need another kind of constructor. So pub fn, let's call it with adder, and it takes an adder of type, it's going to be U64, and it's going to return a self. And so self, and let's adder will be equal to the adder that we passed it. And we also need a getter function, so to be able to get the value out of the address. So pub fn, and it takes a self, and we return self dot adder from it. We'll write syntax error, oh sorry, my bad. This is the right syntax, right? And I guess this is not working because we haven't added it to the mod rs. So let me open nvim cd. So in here we need to add the virtual address as well. So pub mod virtual address, right, quit, let's open it again and say virtual address. Yeah, so the syntax highlighting works. What's the issue? Oh, so I'm not returning, I didn't specify the return type. It's going to return U64. All right. And since we want to play around with this address, we should implement some methods. We want to do standard operations on virtual addresses, like I want to increment a virtual address, decrement it, and we need to be able to compare the object of this struct with other objects of this struct. So we want to basically override the operators. So the equal to operator greater than equal to. So if this code were in Java, I would tell you to implement the comparable and iterable interfaces for this class. But in Rust, we don't have that. What is it saying? Try adding impl default for virtual address. So we'll do that as well. Let's impl default for virtual address and fn default, and let's call self new in this, and that will return the new object. All right. As I said, if this were Java, I would want you to implement the comparable and the comparator interfaces. We don't have that in Rust. We instead have other uh, traits that we can implement. So we'll do that. The first thing we need to do is, as I said, we want to increment, decrement these operators. We want basically those operators to be overridden for this struct. So we'll start doing that. Let's impl std ops, and we'll implement the add operator for it, and it takes an i64 because we can possibly give it a negative value. In that case, it will decrement. So we'll implement it for virtual adder, and from this, so in this we have to implement the add function, and this add function takes a self and an offset. The offset is i64, as I said, and it returns a new virtual address. So virtual address with adder, and to it I pass self dot adder. Need to typecast it to i64 and then add the offset as u64, typecasted back, and it expects an item. Oh, sorry. Not all trait items implemented. It's missing the output. Implement the missing item, type output. Oh, so we need to give it a type. We need to define the type as well. So type output equals to, it's just going to return a virtual adder, and it expects a semicolon, and that's it. That will override the addition operator for us. My bad, guys. We shouldn't be doing this. This will cause precision issues. So what will happen is, since we typecasted to i64 and then typecasted back to u64, that will cause some precision loss in case of high numbers, because max of u64 is way greater than max of i64. So we should not be doing this. Instead, Rust has that functionality built in. It allows us to add i64 through self dot adder underscore dot. We can call the wrapping underscore add this function signed, and to this we can pass in the signed integer instead. So the signed integer for us is the offset, and that will handle the wrapping around value, like, so it won't cause precision loss. This method won't do that. So we can write it back, and so that implemented the add for us, but we also need to implement the subtract. So wait a minute, let me just copy all of this. So that's 1, 2, 3, 4, 5, 6. So 6 y and then p, and instead of add, we'll implement the sub for virtual adder, and the type remains same, but instead of add here we have the sub function like so, and instead of wrapping add signed we'll call the wrapping sub signed. So wrapping sub signed, the rest everything remains the same, and I can remove this. So that handles the plus operator for us, this handles the minus for us, but I also want the plus, wait, the plus equal to and the minus equal to. So for plus equal to, we can implement the add assign trait. So let's copy 6 lines again, 6 y, paste it. Yeah. And instead of sub, let's implement add assign, and instead of sub, uh, this has add underscore assign function, and instead of creating a new object we will update the existing object. So self dot adder underscore equal to, doesn't it need to be mutable? Yeah, so in that case self needs to be mutable. So let's do that, mute, and I guess rest everything remains. Type output is not a member, so we can remove this. Let's write this, and mismatch types expected virtual adder. Does it return a virtual adder? It doesn't return anything. We are updating the existing object, right? So we can remove this as well. Remove this, and so that's add assign for us, but we also want the subtract assign. So 1, 2, 3, 4, 5. 5 y, and then let's come and paste it here. So instead of add assign, I want to implement now the sub assign, and instead of add here, it will be sub, it will be mutable, and oh my bad guys, this here needs to be add signed, and this here needs to be sub signed, and add a semicolon here. We're not returning anything, so add a semicolon. Huh. So now I also want to implement other operators, that is basically for comparison. I want the equal to operator implemented, basically double equal to. New vim displays it like this, two solid lines. I also want the not equal to operator, and I also want so that an object is reflexive, basically equal to a should be true, and we want the following. Oh my god, bruh. I want the not equal to operator. I want the object to be reflexive, as in a should be equal to a. Then I want the greater than, the less than, the greater than, equal to operators, and the less than equal to operators to work for me. Uh, all of this can be done by simply deriving all of these for the struct. So all these operators work through simple derivation, but we can also add one more thing, that is basically in Java you have that dot equal to function, right? You can add a similar thing in Rust. In Rust we have the dot cmp, which is basically compare, and you can also derive that through the odd, was it odd, let me check. Yes, by deriving odd for our struct, and partial odd is what gives us these greater than, less than, greater than, equal to, less than, equal to functions. So what we can do here is come up to our struct uh, right here, and we can derive, we'll derive uh, partial EQ, partial odd, and odd, unmatched brace. All right, so let me try to build it once. Cargo build. So it built fine. We are doing all of this rigmarole to be able to read the instruction pointer register and create an object of this struct that we created, this virtual address struct. And we'll do that in the process. So let me add a function to create this object. So let's go to process, and at the end of it, we'll implement a function basically that will be creating the object of virtual address from the rip register, which is instruction pointer register, and let's call it the program count. It's also called program counter colloquially. So we'll create a function called pub unsafe fn get instruction pointer pointer va for virtual address, and it takes a mutable of self, and it will return a result of vir virtual address, comma, and in case of error we'll return a string saying we could not retrieve the instruction pointer. And in here what we'll do is we'll extract we need to get the value of the rip register. So let rip val equal to self dot proc registers dot get register val by id, and in this id we'll pass in the id of the rip register. So register id of uh, rip, that's the id of the instruction pointer register, and then we'll unwrap it. All right, let's match on this rip val, and what does this return actually? GD, this returns a result of register value. It returns a result of register value. Okay. So for the rip register, we expect a U64 from it so that we can create a virtual address. So if we get a register value of U64, then we're good. In that case, what I can do is create the object of virtual address, and we know virtual address with adder, and to this I will pass the val that we have. Otherwise, if we didn't get this, we'll return an error saying invalid register value returned. Register value returned, and this will return a result. All right, so let's try to write it. Let's try to build it. Cargo build. It works fine, I guess. We won't know it until we test. So to be able to test this, let's go to the main function, main rs, and in here, whenever we do control D, we will also print the virtual address so that the user is able to see at what address what was the instruction being executed when they stopped the debugger. So what you can do is uh, get, wait a minute, process. It is unsafe, right? Yeah. So in here, we need to make it unsafe. And when we say exiting debugger, we will also print the value of the instruction pointer. So let instruction pointer be equal to process dot get instruction pointer virtual address, and if let OK of virtual address equal to IP, in that case, let's println a longest line, and let's also print line the virtual address. VA, it's an object of virtual adder. So dot, uh, the getter was called adder, right? Yeah, adder. Let's write and quit. Let's see if it works. Cargo build. I guess it does. Now let's try to run it. Cargo run yes. So our debugger is running right now, and when I press Ctrl D, it prints the virtual address of the instruction pointer. So that's what we wanted to do. So right now our code is correctly reading the value of the instruction pointer and creating an object of the virtual address out of it. So that's it for this video. We will start playing around with these virtual addresses going forward, and that's it. I'll see you in the next one.